All right, so I'm going to take a few moments to go through the Sing with Sound Lab tour. So first name Mr., last name Rainey. No, it's not my first name, but do it. Okay, so when you move to the next page, it's going to do this Sound Lab. So the sound is all around us. There are many different sounds, but from the loudest boom to the softest rustle, they are all produced the same way. You're going to go into this Sound Lab. Where's the link? Here we go. Now let's open it up in a new tab. Then I'm going to bounce back and forth between the two as it gets set up. Sorry, my computer's a little slow for loading today. So what we can see is here is we'll just do the readings initially and then we'll answer the questions. All right. Perhaps I should have paused the video while this loads. Perhaps I will. I'm going to pause this, and when it finishes loading, I'll be right back. All right, and I'm back. So we're going to hit the start button. It should open. Okay, it sounds like a gerbil having a heart attack. So sound is all around us. There are many different sounds, from the loudest boom to the softest rustle. They are all produced the same way. When something vibrates, it disturbs the air around it, creating waves of energy that our ears pick up as sound. Though we can't see sound waves, a microphone can convert them to electrical energy, so they can be viewed on a machine called an oscilloscope. In this way, we can measure their loudness and their pitch, for example. In this tour, we're going to help understand sound. All right, so it says, sound is produced by the vibration of particles. It requires a medium, for example, air, to travel through. Sound cannot travel through a vacuum. Sound travels through the air in the form of a wave that carries energy from one place to another. Select ping to send a sound and observe what happens to the air particles. So we're going to go ahead and hit ping. And we see we create a transverse wave. We can also see that we can create compressions in the air. And you can kind of see the compressions as they move through. And just remember, even though the energy is moving, the one air particle doesn't really move out of place. So come back to our question, what creates sound waves? All sound waves are created vibrations. Okay, what does sound need in order to travel? Sound needs a medium. It has to have something to travel to. Remember, it's vibrating, and it's going to collide into something else and vibrate that. So it needs a medium, either solid, liquid, or a gas. We already pressed ping. And what we noticed was that the particles travel from the left side. They don't travel to the left side. They move back and forth as they transfer energy. So what we noticed was the particles move back and forth. This white dot doesn't move from its location, but the energy itself does travel from left to right. And because this is a compressional wave, the movement of the particles the movement of the particles in the bottom window is parallel in the same direction as the vibration. All right. So we're going to go ahead to the next section. Remember, sound is created by back and forth vibrations. They are called compression waves. The compression wave consists of areas where the particles are more dense or closer together, called compressions, and areas where particles are less dense or further apart, called rarefactions. So we'll go back to our questions. And again, the part of the wave where the particles closer together, because they're compressed together, squeezed together, that is the compression. Okay, and this says show diagram. So they're showing us how each compression would be considered the crest, each rarefaction would be considered the trough of our wave if we were going to try and convert them. So when sound is represented as a transverse wave, the areas of rarefaction, remember those are the bottom layers. So those are going to be my troughs at the wave trough. All right, so we're going to go ahead and close this. See the particles as particles again. And we're going to go to the next and then to answer the question. It says select ping and look at the left of select ping and look at the effect of the compression waves. Then choose the correct answer. So go ahead and click ping. And the sound waves cause the particles to vibrate slower than the sound source, at the same rate as the sound source, or faster than the sound source. Well, because it is traveling through a medium, they're going to travel at the same rate. They're not going to change frequency. They travel at the same rate. So we come back to here. The wave causes particles to vibrate at the same rate as the sound source. All right, now we're going to hit next, and we're going to see sound as a wave. Okay, the series of compressions and rarefaction caused by sound vibrations can be measured by an oscilloscope. The oscilloscope measures frequency, how many vibrations per second, and the amplitude or strength displays this as a graph. So let's see ping again. So where the top part, our bottom part is kind of our actual reality. This is our oscilloscope showing the transverse version of a wave. Okay. So what two things do oscilloscope measure? If I wanted to measure this, I would be able to measure frequency, wavelength, and amplitude. How can I say that? Well, if I look at my graph, let's ping it again. I can see the wavelength, the distance from one wave to the next, and I can see the height of the wave from the equilibrium. Without a timer, it's kind of hard to see frequency because you'd have to know how many waves per second. Okay, the oscilloscope is shown in the top area. I press to see the action. We've seen it in action a couple of times. Okay, so but if I look at let's ping it again. And again, our sound actually travels as a compressional or longitudinal wave. What does our oscilloscope show? Well, oscilloscope shows this curve. Well, it did show this curved wave, and that curved wave is a transverse wave. So an oscilloscope kind of translates a longitudinal compressional wave into a transverse wave because it's easier to find wavelength and amplitude of a transverse wave than it is of a compressional wave. All right, then we're going to go ahead next and answer the questions that follow. So next we go. Okay, so the peaks in the graph correspond to the areas of, so if I show a ping again, okay, the peaks again are and if I want to show my diagram, it would help. The peaks are my crests or my areas of highest compression. So we scroll down. The peaks in the graph correspond to the areas of our highest compression. Okay, click on the next button. And it brings us to frequency. Now, we've talked about frequency. Frequency is the number of waves per second, or they measure as how fast the particles of the medium vibrate when a sound passes through it. It's always measured in hertz. A hertz is 1 vibration per second. Again, we can hear about 20 to 17,000. I've had kids who've registered 20,000, so technically we hear about 20 to 20,000. We hear fast or high frequency tones as high pitch sounds, low frequency tones as low pitch sounds. An example would be middle C on a music scale would be about 256 hertz. So go back. The frequency of the sound is how fast the particles vibrate as the sound waves pass through them. Okay, so let's go ahead and press next. Select ping. We're going to go ahead and close. Let's close the diagram. And press ping. Okay. So here's our waves. Now let's go ahead and upgrade our frequency, and let's see how that makes different. Now, the sounds are any different, but if you look at the waves, the peaks are much closer together. And that makes sense. The higher the frequency, the shorter the wavelength. So the frequency increases, the peaks are closer together. The higher the frequency, the shorter the wavelength. Click next, and then read the next, and click next again. So go ahead and we'll hit next. Wavelength. The sound wave has a repeating pattern of high pressure and low pressure regions. The distance between one area of high pressure and low pressure one area of high pressure and the next area of high pressure, or compression. And compression is its wavelength. The sound with a long wavelength has a low frequency and therefore a low pitch. So again, as wavelength gets shorter, they're related. The shorter the wavelength, the higher the frequency. If the waves are shorter, more can pass by every second. That's a higher frequency. All right, let's go here and go next again. And we can here, I'll give you an example real quick. So here's my wavelength. If I increase my wavelength, you notice I cannot increase my wavelength without changing my frequency. And it actually has different pitch as well. Okay? So we select ping, user controls, increase and decrease the wavelength. So let's increase the wavelength to 227. Longer wavelength means a lower frequency and lower pitch. User controls the increase, finally, okay. So as wavelength gets shorter, frequency is going to get higher. The shorter the waves are, the more waves can pass by every second. All right. Go ahead and click next. Okay, we've seen the frequency. The shorter the wavelength, the higher the frequency. Frequency and wavelength are related by the formula of velocity, the speed of sound in meters per second, is equal to the frequency times the wavelength. We will not calculate that. Please don't worry about calculating that. However, if I wanted to find the speed of sound through air as 340 meters per second, the sound is traveling through the air with a frequency of 150 hertz. The wavelength would be, and it actually shows me I picked the right one, that would be 227 centimeters. I don't think that's a question. Nope. All right, so that is wavelength and frequency. Next one is going to be amplitude. The amplitude of a sound wave means its volume or its loudness. The stronger the vibration, the higher the sound pressure, and the lower the noise. We measure amplitude in decibels. Change the amplitude and observe the change in the vibration of the wave graph. The decibel scale is logarithmic based on the power of 10 because of the wide range of sound intensities. So we perceive a loud rock group at 120 decibels to be twice as loud as a normal conversation of 60 decibels. But in fact, the sound is 1,000 times more. So for each one of those 10, it's I will never ask you to convert decibels versus times of intensity. But I can play around with amplitude. So let's go ahead and send a ping. My amplitude's at 30. We can see the height of the resting position is about here. Let's go ahead and kick that up a little bit to about 90. And I want you to watch the wave height. Remember, amplitude is wave height. Look at it. Now I'm taking up a much larger space of my oscilloscope graph, so I can see that as I increase the amplitude, I increase the volume. Okay, and then I follow the directions. Follow the directions to observe how amplitude affects the. Okay, so we're going to go ahead and click the directions to next. If a whisper is 20 decibels and the rustle of leaves is 10, remember, every 10 decibels is 10 times the intensity. Oh, okay, I tried it again. I apologize. Why are we 1,000 times? Wait a second. That doesn't make any sense. That one made no sense. All right, well, they said it was multiplied by a factor of 1,000. I would disagree with that, but we're not having a question about that anyway. But just remember that. Oh, okay, so here we are. Now, the next thing we're talking about is the medium. We talked about this. The medium is whatever the wave is traveling through. We usually think of the air as a medium through which sound travels, but it can also travel through liquids as well as solids, such as wood and steel. Sound travels faster through denser materials or mediums, but more energy is often required to make the particles of the medium vibrate. Change the medium and test the speed of the sound in 3 different mediums. So we're going to go in air. We're going to set a ping. Sound is 340 meters per second. Okay, we're going to change it to water. Now notice that as I change it to water, my sound moves much faster, 1,480 meters per second. So let's watch it through water. Okay. And finally, if I move it to solid, it's going to move at 6,420 meters per second. I don't think it's going to change. We see it has to push a lot farther to make that same emphasis. I don't want to paint any more stuff. Okay, so change the medium. We observe the effects of the speed of sound. Make sure to test all 4 different settings for medium. I only tested 3, so let's see what the last one is. Probably glass. Well, vacuum. All right, so if I'll pause a second. I'm just going to ask the question: how fast will this sound wave travel through a vacuum? The answer should have been, it won't travel at all. There's no medium to push. So if there's no medium to push, it's not going to be able to move that wave. So sound travels fastest. The denser the material, the faster the sound wave travels. So it traveled faster through steel, whereas the vacuum did not allow that air wave to travel at all. All right, that is the first page. Okay, use the following link to watch the video and checking to see what you understand with a test yourself quiz at the end, then answer the questions within the form. So we're going to go to Study Jams, which will open up a new link. It is sound, so we're going to go ahead and play the video.
Whoa, Sam! That sculpture's amazing! How do you balance all those things?
Just gotta be very careful. Oh no!
That jackhammer's making the whole table shake!
I know! It's so loud I can feel it!
Phew, it stopped. But not before ruining your sculpture. Sorry, Sam. Just goes to show, sound is more than just what you hear. It's a whole world of vibrations.
How can sound be vibrations? It's noise.
Check it out. When you clap your hands together, or when that jackhammer hits the ground, it makes air move. In waves. Sound waves, to be exact.
Like ocean waves?
Well, kind of. Sound waves travel through the air, but they carry energy like ocean waves do. That energy is what makes an echo.
Really?
Definitely. When moving sound waves hit a surface, like a mountain or even a wall, the energy bounces off and comes back at us. That's the echo.
Cool.
But there's much more to sound waves than just energy. They have different pitches, frequencies, and volumes.
Huh? You're losing me.
Okay, think about the gazillion sounds around us.
Yeah, like birds sound totally different from gorillas, and tea kettles sound different from tubas.
Right. Their sounds have different pitches, high and low.
So what makes them that way?
High-pitched sounds have a high frequency. That means their sound waves vibrate quickly, and there are lots of waves per second, so we hear a higher pitch.
And low-pitched sounds have a low frequency?
Right. Fewer waves per second.
Well, that jackhammer was definitely low, but it was also loud. Wouldn't that make it a high frequency?
Not quite. Volume's a totally different thing. It's the loudness or softness of a sound. The louder the volume, the higher the wave. That's called amplitude.
Like altitude, only for sound. So, how loud is that jackhammer? I mean, compared to other things.
I'd say it's about 105 decibels.
Decimals?
No, decibels. Volume's measured in decibels. The louder the sound, the more decibels. An airplane taking off is 140 decibels, and a crying baby is 110.
Whoa, no wonder my little cousin gives me a headache. I gotta teach him how to whisper.
Yeah, a regular conversation's about 65 decibels, but whispering's only 0 to 5.
Hey, are there any sounds that are lower than 0 decibels?
Yep, humans can't hear them, but we think animals can. They're caused by giant explosions or waves in the ocean. In fact, scientists are studying them.
For what?
To help us predict when a volcano might erupt or if a tsunami's coming.
I can't believe how much goes on behind the scenes when it comes to sound. Who knew that sounds are vibrations that travel in waves, and that frequency tells us the number of waves in a second? It makes sense that frequency goes with pitch, or the highness or lowness of sounds. The volume of a sound is how loud or soft it is, and is measured in decibels. High sounds, low sounds, birds, and bass guitars.
Speaking of noise, it sounds like that jackhammer's done for the day. How about I help you put your sculpture back together?
Wow, thanks. That'd be great. I'll just put on some music.
Sam, remember what happened to loud sounds?
All right. How about we try some classical music?
Let's do the test. What role does energy play in sound? Sound waves have nothing to do with energy. Sound waves carry energy. Energy is present in loud sounds only. Energy is present in high-pitched sounds, but not low-pitched sounds. All sounds carry energy. Remember, an echo is when sound waves bounce off of the surface. What sort of frequency do high-pitched waves or sounds have? The higher the frequency, the higher the pitch. What does volume measure? Volume measures the amplitude or the loudness or softness of the sound. What causes sounds that are lower than 0 decibels? Probably just, we don't know. We're studying the larger explosions like dogs can perceive. Which two aspects of sounds go together? It should be pitch and frequency. And amplitude measures volume. All right, so if we go back to the actual scene with sound waves carry energy. Remember, echo is the reflection of a sound waves reflecting off, bouncing off the surface. What sort of frequency do high-pitched sound waves have? High frequencies have high pitches. Volume measures the loudness or softness. Two aspects of sound that go together are pitch and frequency. And amplitude measures its volume. So hopefully that helps you go through this this activity. This will be an application grade, so please make sure you follow along correctly. And otherwise, have a good rest of your day.